Here's an airplane born of war but tailored for peace. It may never see combat, may never carry a box score on its nose, may never down an enemy. But this modern plane was developed to meet the specific training requirements of the United States Army. In this plane, the pilot makes the transition from single-engine planes to the heavier bomber types. The navigator learns to chart his course. The student bombardier calls out his first bombs away. The photographer trains for aerial work over enemy territory. And in special turret-equipped models, the gunner learns to protect his plane and its crew. Although designed for a specific purpose, the AT-21 is a versatile plane, adaptable to a variety of uses. Its many unusual engineering characteristics result from the knowledge, skill, and facilities of all 5 activities of the Fairchild Engine and Airplane Corporation. Fairchild Aircraft, Ranger Aircraft Engines, Duramold, the Alfin Corporation, and the Stratus Corporation. This model has a speed of 215 miles per hour at sea level. A high-altitude model which can operate from airports, regardless of their location, is also available. It has a maximum speed of 265 miles per hour at critical altitudes and a service ceiling of 30,000 feet. This unusual speed, considering the plane's comparatively low power rating, is due largely to exceptionally clean lines and the absence of rivets and joints used in older types of aircraft. The AT-21 has one of the smoothest surfaces known, a surface made possible by the new Duramold process developed by Fairchild. Through this process, strong panels of bonded wood can be used in virtually every part of aircraft construction, as well as for a host of products in other fields. The fiber of any ordinary veneer, such as poplar, is strong and tough, but it breaks easily with the grain. In the Duramold process, the strips are laid side by side with the grain running in the same direction, then covered with a sheet of phenolic resin glue. Next, a layer of mahogany veneers is laid on top of the glue, with the mahogany grain running at right angles to the poplar. Thus, the qualities of both woods are combined, and cross-graining forms a composite structure of unusual rigidity and durability. In Duramold bonding, glue joints are stronger than the wood itself. This finished piece shows how the many layers of wood are cross-grained to create great strength. In this steel die, the veneer sheets are laid up to form an entire half of the fuselage skin. As in the demonstration, each layer of veneer is covered with a sheet of glue and the next layer placed on top, with the grain running at right angles to the wood underneath. Using production line methods, Fairchild has cut the original time of this operation to 1/10, and the cost to 1/6 of that required when the process was originated. After the skin is laid up, the veneers are first covered with paper, then sealed with a rubber blanket, which has replaced the more cumbersome bag method to make the entire unit airtight. The die is then rolled to one of the many huge cooking chambers known as autoclaves, where all the air is evacuated and layers of wood and glue are literally cooked. Here, heat and pressure force the glue deep into the wood, forming an impervious, waterproof bond. The required cooking time depends on the number of layers of veneer, so skilled operators regulate the temperature and pressure to secure uniform bonding throughout the materials. After the door is closed, the steam pressure is applied. Out of the autoclave, the die is uncovered. Cooking the many separate pieces of veneer fuses them into a single complete section of Duramold skin, ready for installation on the fuselage frame. In the Fairchild laboratory, samples of Duramold skin are both boil-tested and dry-tested for shear strength. Taking more than twice the load of 290 pounds required by Army specifications for a piece this size, this sample stood a strain up to 585 pounds before the break. This electronic instrument determines the degree of bonding, another of the many tests made in the laboratory. On a perfect bond, the needle remains in approximately the same position. But with this imperfect piece, selected for demonstration, the needle swings sharply, indicating an inferior bond between the layers of wood. Duramold is ideal for a wide variety of purposes. This tail cone being laid up on a simple wood die is a sample of the many complex patterns which can be obtained. The expensive dies and equipment required for metal nacelles, tail pieces, and covering sections can be eliminated with the Duramold method, which permits easy fabrication of compound curvatures and unusual shapes. This fuselage skin has been forcibly punctured to show how easily and quickly a damaged piece of Duramold can be repaired, with even a simple field unit known as the Dura Repair Kit. The workman first removes the jagged edges and inscribes a circle around the injured area. Then, with an abrasive tool, he scarfs or bevels the edges from the inscribed line to the hole, exposing the many layers of cross-grained wood that make up the skin. Next, a tracing of the area is prepared, and a patch is made from another piece of Duramold. The many cross-grained layers in the patch correspond to those in the original. The patch is scarfed and affixed to the damaged area with a special liquid glue. After all the air has been exhausted with a small pump, the simple heating unit from the field kit is plugged into any 110-volt outlet, and a perfect restoration is completed in a few minutes. The entire operation has been done without any elaborate materials or special equipment other than the Dura Repair Kit. After sanding and painting, the patched area cannot be distinguished from the original skin. Bonding deep glue joints by means of high-frequency electrical current is another exclusive Duramold development. The individual strips that make up a wing spar are fed through the glue machine, then placed in a separate form where special thermosetting glue dries fast and becomes insolvent. Former methods of heating by external application were sufficient for the outside of the joint, but the heat could not penetrate deep enough into the fibers. In the Duramold process, the form is closed and as much as 30,000 watts of electrical current are shot into the wood, where it generates its own bonding heat inside the joint structure and bonds outward from the center of the wood. This fluorescent tube, which lights by induction alone, indicates the extent of the high-frequency field. By this modern method, a complete wing spar can be bonded in less than 30 minutes. Certain assembly operations require a cold-setting synthetic resin glue which must be kept fresh and can be used for only 2 hours at a time. The glue is taken from cups whose colors match the lights on boards posted throughout the plant. When any of the 2-hour periods of usefulness expires, the lights change, and a new supply of glue in correspondingly colored cups is distributed to the workers. A Duramold fuselage skin, which has been previously bonded in the autoclave, is now installed on the forward section of an AT-21. Extremely lightweight and pliable, it fits like a glove, and together with a similar skin on the other side, is speedily glued to the wood bulkhead. Here on the large fuselage assembly portion of the Fairchild factory, all operations are done with modern jigs, fixtures, and other production machinery designed to cut production time. The AT-21 is powered by two 12-cylinder inverted V-type air-cooled engines with less frontal area than comparable radial engines, thus affording higher speed. At Farmingdale, Long Island, in Fairchild's Ranger Engine Division, years of patient research and experimentation go into every engine. This machine determines the stress on gear teeth in various positions. Exact plastic copies of gears are made, and when viewed under polarized light, the points of strain are clearly shown. As the strain increases, the radiation of stress is visible. Cross-section samples of materials are studied under a microphotometer to determine their microscopic structure and then photographed on film for further study. With this three-dimensional viewer, X-ray pictures of Ranger castings are examined to discover possible hidden imperfections. A spectrograph defines and detects the component parts of materials and gives a complete qualitative analysis in 30 minutes. A photoelectric eye measures the recording and determines the quantity of the various elements in the material tested. Here, a powerful microscope shows how a liquid used for preserving manganese castings crystallizes and forms a protective coating on the metal. Ranger engines are cooled by a system of pressure baffles. The air enters the front of the engine between the banks of cylinders, is distributed evenly throughout all the cylinders, then finally expelled from the back of the engine. Another exclusive Fairchild feature is a method for bonding pure aluminum fins to the steel cylinder barrels of Ranger engines. Known as the Alfin Process, this method makes a perfect union between the aluminum and the steel. When conventional methods of shrinking aluminum alloy fins to steel cylinder barrels is used, tiny spaces of dead air exist in the bond and cause slower dissipation of heat. The perfect bond produced by the Alfin process affords efficient heat conduction throughout the entire area. This process has many applications on both large and small engines. It can also solve problems of heat transfer in many varied industrial fields. As this chart shows, in conventional engines, a high percentage of power is required for cooling as the horsepower increases. But in the Ranger engine, with its Alfin cylinders, the percentage of cooling power required is considerably less. The Ranger division uses specially designed manufacturing methods and tools throughout the plant. This multiple spindle drill with its 185 spindles drills all the holes in both the front and rear crankcase sections in a few seconds. The multiple spindle drill is only one of many high-speed, multiple process tools that help speed the production of Ranger engines. Precision production of this type allows for interchangeability of parts between engines. In assembling the Ranger 12, half the crankcase is first placed in a movable cradle, where it is fitted with crankshaft and connecting rods. Next, the other half of the crankcase is placed in position, and the nuts are turned with a special speed wrench, which automatically tightens them to a specific tension. These wrenches, as well as other power tools, are suspended from an overhead trolley to speed production. The assembly is now turned over, and the front gear case containing the propeller shaft and the reduction gears is fitted into place. Following the installation of the gear case, the banks of Alfin cylinders are fitted over the pistons. And now the rear accessory housing containing the gears that drive the generator, the magnetos, and all other accessories goes on. Camshaft and rocker arm supports are next. Then the camshafts are put in place and the cam box covers are bolted on. Finally, the radio-shielded ignition harnesses and exhaust stacks are put into place to finish the assembly. When completed, the engine is wheeled off the assembly line and into one of the many test cells at the Ranger plant, where it is given an 8-hour test run. In addition to many other exhaustive tests, the engines are subjected to extreme temperatures of heat and cold. During the test, records are made on fuel consumption, oil pressure, manifold pressure, and temperature readings. A complete and permanent transcript is kept of every detail, and after the test, the records are carefully analyzed to determine if adjustments to the engine are necessary. Following this initial test run, each Ranger is completely torn down, and every part is carefully inspected before the engines are reassembled and prepared for shipment. The result is an efficient, smooth operating power plant. Covered by a coat of transparent plyofilm to protect it from moisture and dirt, the Ranger engine is truly a modern package of power. Back at the Fairchild division, the engines are completely mounted, ready for quick installation in the planes. Each one is fitted with cowlings to permit change of entire power units in a few minutes. The actual installation is a smooth, simple operation. In the final stages of assembly, the plane is fitted with wings, tail surfaces, landing gear, and all other equipment, including the pilot's controls and the plexiglass nose section. Before leaving the plant, each plane is thoroughly inspected from top to bottom and from stem to stern. When completed, every new plane is taken to the field for its first hop, where an experienced flight test crew puts it through its paces. In the roomy pilot compartment, the conveniently arranged instrument panel has all the instruments properly grouped for easy reading. As the engines are warmed up, each of them is given a last-minute check. Maximum visibility over the top of the engines is a distinct advantage of Ranger's streamlined design. The pilot can see the mechanic, even when the latter is working in close to the engine nacelle. The visibility feature is further extended to allow an almost unlimited view of both sides, as well as up and down. The pilot can see any obstacles in his path while taxiing the ship, as demonstrated by the small Fairchild plane in front of this AT-21, as it taxis out for the first takeoff. As the plane speeds down the runway, the tricycle landing gear keeps it perfectly steady. Even in a strong crosswind, there is no tendency to swerve to one side. Carrying a full load, the ship clears the ground in less than 1,300 feet. Once in the air, the AT-21 climbs at the rate of 1,000 feet a minute. In flight, the visibility from an AT-21 aids as much in the operation of the ship as it did on the ground. As another AT-21 approaches the camera ship from the rear, the pilot has a continuous clear view of it as it passes on the right and streaks over to the left. The ability to perform on only one engine is an important safety feature of these twin-engine airplanes. In this demonstration, the pilot cuts the left engine, and while the propeller windmills from the force of the air, he easily makes a right turn with the power supplied by the remaining engine. The AT-21 has a single engine ceiling of more than 13,000 feet. The wing of this airplane is another distinctly Fairchild development. Designed by Armand Thiblot to have superior stalling characteristics, the AT-21 has one of the safest wings on any airplane flying today. Up it climbs. Then the stall. but the pilot has full aileron control. At full power, the AT-21 stalls at only 70 miles per hour, and with engines idling, it stalls at 80. Now another stall. Pay attention to the strands of yarn attached to the wing as the climb starts. Notice the angle of the horizon. When the speed reaches 70 miles per hour, note the action of the strands. The stall starts on the inside of the wing and works out to the tip, the opposite of most planes. Thus, the AT-21 will not roll nor fall off on one wing without warning in a stall. And full aileron control is maintained at all times. Down it comes, picking up speed out of the stall. This high-altitude ship has superior performance and maneuverability in every respect. An airplane without tricks, the AT-21 is smooth, easy to fly, and equally easy to land. Down come the wheels. In landing, the AT-21's excellent visibility is again a big advantage to the pilot. Down and dead ahead, he has a full view of the entire runway at all times. The long-stroke gear gently eases the plane onto the ground, and the landing run is straight and short. The hydraulic brakes can bring the ship to a stop within 800 feet. Easy to steer, the AT-21 is just as maneuverable on the ground as it is in the air. The first trainer to be equipped with tricycle landing gear. This feature enables the plane to maintain an even keel even on rough fields, while the powerful brakes provide maximum safety. Thus, the pilot has complete ground control of the ship. Fairchild's far-seeing design and intelligent planning have produced an airplane that is easy to maintain and service. Specially designed cowlings make the engines readily accessible. With 4 separate fuel tanks located in the wings and its efficient supercharged engines, the plane has a non-stop range of 800 miles. In an emergency, large, readily accessible hatches can be opened quickly. The AT-21's many unusual characteristics make it an ideal airplane for many varied purposes. In war or in peace, it is an efficient military trainer, a fast, dependable patrol ship, a compact military transport for a wide variety of tactical missions. And if the need arises, it is an excellent light bomber, equally useful in freezing temperatures or tropical climates. When converted to a special purpose military transport, the AT-21's roomy cabin affords ample accommodations for executive officers to confer as they fly comfortably and swiftly between widely separated bases. Or by removing the seats, the cabin becomes an emergency military cargo carrier. This all-purpose, high-altitude airplane of unique construction and design opens new horizons in aircraft development. With the AT-21, many military problems can be solved more economically and more efficiently. For this great new plane is truly representative of Fairchild's touch of tomorrow in the planes of today.